Okay, so as I was saying, for a three-dimensional wing, there is a relation between the lift and drag forces, and that's because when you have more lift, there will be more wingtip vortices, and that means there will be more drag force. And to see this experimentally, you can take a wing and put it in a wind tunnel, then measure its lift and drag forces as follows. So, for example, for this condition, you obtain a certain lift and drag coefficient. So this should be CL1 and CL2. CL1 and CD1, I'm sorry. Okay, and then you repeat the test at a different angle of attack, and you get a different CL-CD pair. Okay, so you do this a number of times. You scan a certain angle of attack range, and then you put all these numbers you found on a graph. So let horizontal axis be the lift coefficient, and the vertical axis be the drag coefficient. So first, let's say you find the angle where the lift force is 0. So if you have a symmetric airfoil, then that should happen at 0-degree angle of attack. But if you have a cambered airfoil, then the angle where the lift force is 0 should be some negative angle of attack. So you make this table, and so you first, let me make this alpha 1, and then this becomes a point here. Okay, so you take the point and put it. So for example, your first point is the point where the lift coefficient is 0. So this is the 0 point for the lift coefficient. And then so you make all these tests, and then you put all these values on a chart. Okay, so as I said, as the lift coefficient is increased, you expect the drag coefficient to increase as well. And that's what you really see in an experiment. If you if you have a proper experiment set up where your measurements are correct, you see such a trend. In fact, all the experiments performed, all the proper experiments performed for different designs, different airfoil designs and different wing designs show such a parabolic variation. Okay, so when you make all these experiments, you see that the drag coefficient changes with the square of the lift coefficient. That's what why I call it parabolic. So here you see 3 sample data. These are for 3 different wing designs, but they all show a parabolic relation. So they're not all the same, obviously, because they are different wings, but they all share the same characteristic, that if the lift force is increased, the drag force increases by its square. So if you look at all these data, then you see that you can use such an expression for the drag coefficient. So the equation for all these curves look like this. Okay, so there's a square term which gives this parabolic relation, and then there's some constant term, and the constant term should be there because when the lift force is 0, so you have there's a non-zero drag coefficient. There's a non-zero drag coefficient here, so to get that effect you need to have such a constant term. So this is what you see in experiments, but there's a theoretical explanation for this as well. I'm not going to go into the details of that, but if you're interested, you can search online and you can read more about the relation between drag and lift coefficients. in fact, there are books written on the drag force. So the entire book devoted to explaining how drag force is created and how it changes with various parameters. Okay, so by looking at these experimental data and theoretical results, so you know that your equation should look like this. Now the next question is, how should I choose these values, A and B values? If you have experimental data, then you can find these coefficients from the data by curve fitting, right? So you can find the most suitable values for these A and B coefficients that fits the experimental data best using curve fitting. Okay? So if these red crosses are your test values, then you can find the best A and B values that gives you the parabolic curve that passes closest to all these points. But obviously these values depend on your aircraft design. So if you have a different design, your curve will look different. That means the A and B values will be different depending on how different your aircraft design is. So out of these three designs, which one do you think is the best in terms of aerodynamic performance? Bunu diyorsun yani. You think this is the best one? Does everybody agree with that? The important thing is, as I said before, the ratio of the two. You want large lift force, but you want small drag force. And if you compare these three designs, then this red one really gives you the best performance in that sense. Because if this is, for example, the lift coefficient you need, then the red curve gives you the lowest drag coefficient for the same amount of lift coefficient. So let's choose this point. So this is what you want. Let me call this CL1. And the lowest drag coefficient is given by this red wing. And if you compare the two, and this green one is much worse because the drag coefficient you have for the same lift coefficient is much higher. Okay, so obviously this red data is the best aerodynamic design. Okay, so the A coefficient in the parabolic equation is for the drag that exists even when there is no lift force, and the B coefficient shows how much drag is increased when there is lift force, which is related to the three-dimensional design. And effects of the planform shape and aspect ratio are both included in the B coefficient. So here I rewrote that equation, and instead of A I just call CD0, and the B I called it K here, where this coefficient K is a function of planform shape and aspect ratio. So this part is the induced drag coefficient, CDI. That depends on the lift coefficient and the aircraft design, and the aircraft design is included in this K number. So this equation is called the drag polar equation. The equation that relates the drag coefficient to the lift coefficient is called the drag polar equation, and it is in the form of a parabola. You can use this for our calculations in this course. And in the textbook it says the drag polar of an aircraft contains almost all the information required to analyze its performance and hence to begin a design. So I told you this before. So this equation is the most important equation in aircraft performance. So if you have an aircraft then the performance will be improved if you have a better aerodynamic efficiency, and that is given by this equation. So normally you can make anything fly. If you have enough power, enough thrust force, you can make an aircraft out of this desk, for example, right? So this desk doesn't look anything like an aircraft, but you can fly it if you have powerful enough engines. But the thing is, if you have to use a big engine, then that means you will have to burn more fuel as well. That means you have to carry more fuel, and if you are carrying more fuel, then the amount of useful cargo you can carry will be reduced. And to be able to carry more cargo, you need to make everything larger. That means your engine needs to be even larger, so everything is related to each other. And to find the best performance in this circular argument is to find a way to make this K coefficient as small as possible. Okay, so let me give you this additional information that so in this course, this is what we will use for the drag coefficient. We will use this equation, but normally there's a third component in that equation, and in addition to the parasite drag and induced drag coefficients, you can add a wave drag coefficient, and this CdW represents compressibility effects, and that can get very large when there are shock waves. So if you are flying close to the speed of the sound, then this part will be the dominant part. But in this course, we assume that the flow is incompressible and we ignore this part. Okay, so in this course, we will be using this part of the equation and ignore this part. Okay, so I said that the shape of the planform and the aspect ratio of the wing, everything is included into this parameter. Now let me talk about how these things, the effect of these things can be added into this K parameter. Okay, so previously we already discussed the effect of the aspect ratio. So hopefully I convinced you that if you have a high aspect ratio, that is a good thing for aerodynamic efficiency. So let's put the effect of aspect ratio outside the equation. Now let's consider the shape of the planform. So let me add okay, so we already discussed that high aspect ratio is good for aerodynamic efficiency. So let's keep aspect ratio fixed and consider the effect of the planform shape. The planform shape on aerodynamic efficiency. So let's consider many different planform shapes. All have the same aspect ratio, but the planform shapes are different. So this is a rectangular planform. This is a trapezoidal planform. So what else we can have? You can have a high sweep wing, something like this. Or you can have a delta wing. You can have a compound wing, right? So çok simetrik olmadı ama. And let me also draw an elliptical one. Okay, so imagine all these wings have the same aspect ratio. So the aspect ratio is not the reason why these have different performances. Well, obviously they have different platform shapes. And if you make small models of all of these designs and you test them in a wind tunnel, you will see you'll get such results, right? Some of them will be bad, some of them will be better than the others, and somehow we need to be able to compare these wings, the performances of these wings. So we know that they all will have different K values. So this will be K1, K3, K4, and K6. And again, some experimental studies and some theoretical studies show that out of all possible planform shapes, the most efficient design is the one that gives an elliptical span-wise lift distribution. Unfortunately, I can't really give you a proof as to why this is the case, but that means so this is the lift distribution, span-wise lift distribution. So this is the front view of a wing. This is the lift distribution. So from both theoretical and experimental studies, we know that the best possible aerodynamic efficiency, that means smallest K value, is obtained when the lift distribution is an ellipse. So let me make this smaller so that it fits here. Olur. Okay, so now when designing the wing planform, the goal is to achieve this optimum lift distribution, which is an ellipse. And one obvious way to achieve elliptic lift distribution is to have the wing planform in the shape of an ellipse. So if you make the wing planform in the shape of an ellipse, that gives you an elliptical lift distribution, and that gives you the best possible aerodynamic efficiency. Okay, so in other words, if you compare all these designs, most probably this will give you the best possible aerodynamic efficiency. That means this K6 value will be the smallest among the K values of the other wing designs. In fact, this was known in World War II times, and the British aircraft Spitfire was designed with an elliptical wing design. So I don't know if you heard of this aircraft before, but this is a legendary aircraft, and this was very successful in the Second World War. And the reason it was successful is it had much better performance than the opponent aircraft in the Second World War. And this performance difference is attributed to it having an elliptical wing design. And in the Wikipedia page, they talk about that. So here you see that it has a winged air planform design that is almost a perfect ellipse. And here it says the elliptical wing was decided upon quite early on. Aerodynamically, it was the best for our purpose because for the induced drag that caused in producing lift was lowest when this shape was used. The ellipse was theoretically a perfection. So they knew that the aerodynamically ellipse was a perfect wing design, and that's what they used in design. And as a result, this aircraft had a superiority over all the other aircraft. So it could fly faster, it could climb faster, it could climb to higher altitudes, it could maneuver faster. So it could do everything better than all the other aircraft, and as a result, it was very successful in the Second World War. So even the horizontal tail has an elliptical planform. You see that? Okay, so this is a fact. The elliptical lift distribution gives you the best possible aerodynamic efficiency, and everything else will be less, right? So the K will be worse. That means the K value will be higher for every other possible planform shape. So in the end, they started using this formula to represent the induced drag coefficient as a function of the aircraft design and the lift coefficient. So let me just add a few more stuff here. So normally this CDI you said is equal to K times CL squared. So now this is the K parameter. So there's a pi number here. Again, I don't really know why this pi number goes in there. But the aspect ratio is here directly, and the wing design, the wing planform shape design is added into this E number. Okay, where pi is the mathematical constant, aspect ratio is the aspect ratio of the wing, and E is a non-dimensional number referred to as the Oswald efficiency factor. So effect of the aspect ratio is explicitly included in the K expression. And the effect of the wing planform shape is included in the E parameter. Since the best possible wing design is elliptical, E number is chosen as 1 for the elliptical design, and for any other design it is less than 1. So for a rectangular planform, for example, the E number is approximately 0.7. And for anything else, it will be just a number less than 1. Okay? Okay, so if you have such different wing designs, then to be able to calculate the induced drag coefficient, you need to know the Oswald efficiency factor for each one of these designs. And for this one, you know that E is equal to 1. For rectangular, this is something like 0.7. And this is trapezoidal design. It is better than rectangular, but worse than the elliptical. So for this one, E should be between them. 0.7 is less than E, which is less than 1. You can say the same for all the other designs as well. Okay? So if you are given an aircraft, if you want to study the performance of an aircraft, to use the drag polar information, you need to know this E number. So if you don't know exactly the value of the E number, you can just try to guess as close as possible. So for example, if you know that for a rectangle it should be something like this, and for this you can choose 0.8, for example, is a reasonable assumption. If you don't have anything better to use, then you can just use your best guess to calculate the performance. Okay? So here's just another explanation of the same thing. So you can just read through this. Okay, then you may ask a question. If we know that ellipse is the best possible design, then how come the aircraft that we know today don't have elliptical designs, right? So if you consider the modern airplanes, none of them have an elliptical design. That's because this is considering the fact that the wave drag is ignored. So remember, I said here that normally in the drag equation there is a third component due to the compressibility effect, and if we ignore this part, then it is true that the ellipse B is the best possible design that gives you the most efficient aerodynamic performance. But if compressibility is a concern, then that CDW is in the equation as well, and for that purpose ellipse is not that efficient anymore, and that's why the modern high-speed aircraft have all such angles with wing design with a sweep angle. So for example, this is, I don't know what this is, but it's either a Boeing or an Airbus. And if you look at the wing design, it's not elliptical, obviously. And the reason for this is this sweep angle is necessary to have a high-speed aircraft, and that's why they use that effect. Okay, do you have any questions? Okay, so in our future calculations, we will be using this drag polar equation a lot, and for that we need to calculate this K parameter. So I will either give you the value of the K parameter directly, or I will give you the Oswald efficiency factor for the aircraft I will ask you to study. And once you know that, once you know the value of the K parameter, then that means you know the drag coefficient value, and you need to know the value of the lift coefficient as well, and you'll be using these coefficients in these equations, right? So in the performance calculations we'll be talking about the actual force values and not the non-dimensional coefficients. And to calculate the actual force values, this is the equation we have. So we need to know the value of the dynamic pressure as well. And remember, in the dynamic pressure we have the air density and the speed of the aircraft. So we need to know the value of the air density as well. And air density is not a constant number, obviously. So for water, for example, you can assume the density to be constant, which will be very accurate for pretty much all cases you can think of. But this is not the case. The air density can change significantly, and how the air density changes in the atmosphere is the next topic I would like to talk about. I will be talking about the standard atmosphere that explains how the air properties, including the density and temperature, pressure, change with altitude. But I don't want to start that today. I will be talking about the standard atmosphere on Friday. So if you don't have any further questions, I'm going to stop for today, and I will continue with the standard atmosphere on Friday. Okay, so hopefully Meteor will start working, and I will keep some posting information there, including the lecture notes.